here today already we have discussed one theorem, very important theorem on circle. Today another theorem we'll discuss. But before that, a very important point we'll discuss. That is, with respect to a circle, right? Position of a point with respect to a circle and number of tangents. Number of tangents drawn through that point or from that point. So let us just draw the situations, then it will be easy for us to understand. Let us try to draw that situation. One is this circle. We have three such situations, so I'll draw three circles and then let us just see what are the three situations we can get. We'll be having three situations. We may be getting the point here, say this is the point. We may be getting the point here on the circle, or we may be getting the point outside the circle. These are the three possible situations. Now, in the very first situation, if you observe, there will be no possibility of any tangents, no tangent. That means if the point is in the interior, then you cannot draw any tangent to the circle through that point or from that point, right? But once you have the point on the circle, then exactly one tangent you can draw here. That point. Exactly one tangent can be drawn at that point when the point is on the circle. Only one tangent. Only one tangent. And then if the point is outside, then we have possibility of drawing two tangents. One like this and another this way. So these are the things you have to remember. So here we have two tangents. That means if somebody asks you that if any point is randomly taken in a plane and there is a circle, then how many maximum tangents can be drawn if exist? It will be two. And how many minimum tangents we can draw? It is zero. And zero will be the case when the point will be lying in the interior, and two tangents will be the case when the point will be lying in the exterior. So this is to be understood. Now, here in this particular part only, I would like to explain you one thing, very, very important thing. Please observe that carefully. If I name the point of contact as A and B, then this particular length from the point of contact to the point where the tangent is drawn, this is known as the length of the tangent drawn from P. This two. These are known as the length of the tangents, right? So this is the convention. Otherwise, tangent is a infinite ray, right? But even then, we define the length means this is the convention. PA and PB are the length of the tangent. PA and PB are the length of the tangents. So this is the convention we have. And on this length of a tangent, we have a very important theorem. So I think I can move on to the next page immediately. Very last thing is to be written. Okay, now let us write the theorem. This theorem we have to go for the proof also, because this is important theorem. Exam also it is set normally. Theorem. The lengths of the tangents drawn from an external point to a circle are equal. This is a very fundamental theorem, but very important. That means if you draw, already you came to know that from an external point you can draw two tangents. Both the tangent will have the same length. This is what we have to prove. So for that, I'll draw a figure here, and then we'll try to see how to proceed further. Right. So we'll be taking a point outside. Say this with a point. Suppose this with a point. Say P. From this P, we are going to draw two tangents, and we'll show that the length of these two tangents are equal. So we are going to draw the tangents. You also draw this in your copy. This is one of the tangent. Now it is not discussed how we draw the tangent. We'll see how we draw. There is a construction chapter also. So we'll come to know how to draw this pair of tangents from the point. So here too we have just drawn it. And then this is the center. Let us just mark this center to be say O, and a point of context also we would like to mark. Say this point be A, and this another point B, suppose B. So we have these things done. So now we can write the restatement. First, let me write the restatement. Afterwards, we'll see what are the things we have to generate in order to prove it. Restatement. Let P be any external point and O be the center of the circle. Center of the circle. Of course, you can write it like this also, that let O be the center of the circle and P be any point in the exterior. You can draw like this also. Also, let PA and PB be two tangents from P to the circle at A and B respectively. To show that, what to show? PA equal to PB. This is what we have to show. Now, in this particular simple figure, it will not be possible for us to go for the proof without doing any extra construction. So what we'll do, we are going to join this particular external point to the center, and the point of contact will join to the center. Right? So we'll be getting this. Now very easily, you can remember that they will form the radius, so they will be equal. This is very important. Second important thing is that already you came to know that radius to the point of contact of a tangent is perpendicular to the tangent. So this angle will be equal to this angle, and each of this will be negative. And readily one more part you can find as common. This OP is the common set. Actually, your proof is already very clear. Right? So you have to only show the congruency of these two triangles, PAO and PBO. Then CPCT will give me this. But before that, you write the construction. We need the construction set. Construction is what? Joined OP, OA, and OB. This is what we have joined, nothing else. We simply joined. Now, first of all, you write, we know that the radius through the point of contact of the tangent to a circle is perpendicular to it. Therefore, you talk about directly angle PAO is equal to angle PBO is equal to 90 degree, right? So once you write this, now you can talk about the congruency. Thus, in triangle APO and triangle BPO, you got the right angle equal, that is PAO is equal to PBO. Both are 90 degree. Then you can talk about the hypotenuse, that is PO equal to PO. It is what? Common side. This is P. And at last you will be getting OA equal to OB. It is what? Radii of the circle. So once you get this, what will be your ultimate observation? By RHS congruency, by RHS congruency, triangle PAO is congruent to triangle PBO. Therefore, PA equal to PB. CPCT. Okay, now you see we have few more important points which I'll write as a conclusion afterwards. But first you see what conclusion we can get from here. First let us mark those, right? That I write in the other page. See, now we have already shown that these triangles are congruent, PAO and PBO. So in that case, I can say this angle equals this angle. Again, what is the reason? Simplicity. I can say. Similarly, I can say this also, that this angle 3 is equal to this angle 4. So these are the two important conclusions which we will be getting from, right? So that conclusion I am writing like a note, because they may put this also as a question, right? So I'm writing that as a note here. What is the note? First note. See how we'll write the note. The line segment joining the center of the circle to the external point bisects the angle between the tangents drawn or tangents from the external point, right? Just you see the meaning. This is one. Second one, what? It was bisecting the angle between the radii to the point of contact. So we'll write the same thing. The line segment joining the center of the circle to the external points bisects the angle between the radii, not radius, radii to the point of contact of the tangents drawn from the external point. Drawn from the external point. Okay. To be more precise, you can write to the circle. So you please be very, very alert about this particular point. Right? These are the two very important conclusions which we have to always remember. Right? This is one, and the other one is here. So this, my handwriting is not very good, but still you read it somehow. Right? Now you see again, I'll go back to the previous figure because there are a lot of things which you can get from this previous figure. Okay. Now you try to see. These two angles are 90 each. It means their sum is 180. And we know that in a quadrilateral all four angles has sum which is 60. So remaining two angles will be also having a sum 180. Now, if I just consider this APBO as a separate quadrilateral, which refers to this circle, then I can say that sum of the opposite angles is equal to 180. And that will imply that these particular points are forming a cyclic quadrilateral, right? So that might also be given as a separate question to you. So this also I'll write as a note in the next page, note number 3, which may be set as a separate question. So I'm writing it here like this, giving complete reasoning. Here, that means I'm talking about the figure. PAO, angle PAO plus angle PBO, you look at the figure. Therefore, angle APB plus angle AOB will be equal to 180. Therefore, quadrilateral APBO is cyclic, right? Quadrilateral APBO is cyclic. Okay, if this is cyclic, I can say one more statement also. That is, points A, P, B, O are concyclic. Concyclic means lying on the same circle. So that is a very important part. Again, please make a note of it. Please make a note of it. Very, very important. Right? Okay. So one more observation is there, which actually there is a problem only. In the book only that is a problem. So what is the observation? I'll write just separately here. Actually, this is the observation. It is angle between the tangents and angle between the radii through the point of context are supplementary. So I'll not write that statement. I'll write here. Here, angle APB. This is the angle between the tangents, and this is the angle between the radii through the point of context are supplementary. Already we have written that, but still as a note I just wanted to. So this is the fourth note regarding that particular figure. Now we'll be starting with problems. So I think I can move to the next board. So now we'll be taking problems. I'm not taking the problems from the book serially, but I'm going to take the problems of the book only. Right? So I'll not write the question number of the book here. I'm avoiding my number here. So actually, I'm going to do question number 8 of the book, question number 8 of the exercise, right? I'll be doing the problems in a jumbled way. So here I'm first writing a statement. Simply, I'll write a statement from my side and users correlate with the problem of the book. Book is very directly given in the book. So I'm writing like this. So that the sum of the opposite sides of a quadrilateral circumscribing a circle are equal. Sum of the opposite sides of a quadrilateral are equal. This is the main part. When if it circumscribe a circle. Circumscribe a circle matlab this circle will be kept inside and the quadrilateral will be outside. That is a very important part. It is the question number 8 of your book. So here, first let me draw the figure, then you will easily compare that it is actually the question number 8 only. I might change the points here. I may not be writing that ABCD here. I have to adjust this side, no problem. This is 1. So this is the figure. There is a figure we have drawn. And now here, this with the center of the circumscribing, sorry, inscribed circle. Circle is said to be inscribed and quadrilateral is said to be circumscribing the circle. So here, let me give the name. Suppose this be A, this be B, this be C, and this be D. Right? So here we have got. At the same time, we need to know the point of context also. If we do not know the point of context, then it will be difficult for referring those. So let me name the point. Say this is P, then this point is suppose Q, this point is suppose R, and this point is suppose S. So these are the points of context, right? So let us write first what exactly they are asking you to do. Right? Then we'll try to see what else we have to do with the figure. Sorry, restatement. Let A, B, C, D be a quadrilateral circumscribing the circle with center at O. So we did not mark the center. Let me mark the center. Center is it, right? To show that. See what to show? Sum of the opposite sides are equal. So if I pick one side as AB, its opposite side will be which one? CD. So this is equal to AD plus BC. Now, if you would like to compare, you can compare the problem with your book. It is exactly the same question, question number 8. So now we'll be proceeding for proving it. how we'll prove it. We are going to use the second theorem. Let us start the point A. So from A, you can consider circumscribing. What does it mean actually? The quadrilateral is circumscribing the circle. What is the meaning? Meaning is that circle will be drawn inside the quadrilateral in such a way that it will touch all the four sides. So from A, we are getting these two adjacent side of the quadrilateral as tangents. So our second theorem says that the length of the tangents are equal. So I can get AS equal to AP. Similar reasoning I can give for this two. Similarly for this two and this two. So this time I need to prove this, right? So I do not have to draw any construction. Simply how we will proceed? We will say that we know that theorem. So you state it. We know that the lengths of the tangents drawn. I have got the notification of 10 minutes. Automatically after 10 minutes line will be disconnected. So that will be the end of the class. So length of the tangents from an external point to a circle are equal. Therefore, now we'll be writing the conclusions. What we can write? AS equal to AP. Right. Similarly, I can write, you now write from B, BP equal to BQ. Then you write from C, CQ equal to CR. And at last it is DS equal to DR. So this all equations together you mark it as 1. Okay, so these are the conclusions we got by using the second theorem. Now we are going for the final answer. Now you start with any one of the side, either AB plus CD or AD plus BC. I am starting with AB plus CD. What is AB plus CD telling you from the figure? Just from the figure you see, AB is nothing but sum of AP and BP. Similarly, CD is the sum of CR and DR. If you refer to the figure, easily you can identify. Now you see, AP is equal to whom? AP is equal to AS. BP is equal to whom? BQ. So whatever possible uh, change you can make here by using equation 1, you do this. So this will give you AP equal to AS, then BP equal to BQ, CR is equal to CQ, and DR equal to DS. Very fine. And whenever you use equation 1, indicate that you have used equation 1. And now what you need to do, just last part you have to rearrange, because you need to arrive at AD and you need to arrive at BC. Now just you see from the figure, AD and BC, what are the components? For getting AD, you need AS and you need DS. So you collect AS and DS together. AS is already here, and easily, because these are all sum, you can associate these two. And for the other, there is no option out but to keep these two together. Now look at the figure again. AS plus DS will give you what? AD. And this BQ plus CQ will give you what? BQ plus CQ will give you CD. So ultimately what you have arrived? AB plus CD equal to AD plus, sorry, this is not CD, I'm sorry, it is BC. So AB plus CD equal to AD plus BC. So that's a very good theorem, right? Please write it immediately. I am left out with 6 minutes, so let's see whether I could complete one problem or not. I can do it. If you finish, you inform. I have finished. Okay. So I'm going to go for the next problem. That is question number 11 of your book. Right? Question number 11 of your book. I'll write it as question number 2. So that the parallelogram circumscribing a circle is a rhombus. Why have I chosen it? Because it is the extension of the previous problem only. So I'll do it quickly. So please follow it. You'll be able to write it yourself only. Just follow it. If you are unable to copy also, there is no problem. I have to consider here, of course, when I draw the figure, I have to consider the rhombus only, right? We should not consider parallelogram, because parallelogram will not be possible. If you draw here, it will not be possible. So I will consider a rhombus. This is the rhombus we have drawn. This is the rhombus we have drawn. And now suppose this is the same points I want to use so that I can easily refer to that easily and quickly. This is C and this is the point D, right? So here point of context also you use, here it was P, here it was Q, here it was R, and here it was S. So these are the things, and we use the center of the circle. So I'll not write a restatement here. Now what will happen, for proof, right? From beginning to the last, previous question, whatever you did in the previous question, you write and you drop yourself at this particular answer, right? Because previous question will bring you to this particular answer. Everything you have to write, remember it. This previous question answer, you have to write everything. Then you will come up to here, this you mark as 1. After that, what you write? After that, you can write, but AB equal to CD, AB equal to CD, because it is a parallelogram, opposite sides will be equal. Also, AD will be equal to BC because it is a parallelogram. So, what will be your reason? Since ABCD is a parallelogram, it is given. I have to prove that it is a rhombus, but I am given that it is a parallelogram. So, now make use of this in equation 1. So, I just make both to be AB. So, AB plus AB equal to BC plus BC. That gives you twice AB equal to twice BC, ultimately leading you to be AB equal to BC. Now, if AB equal to BC, just you see, AB it was equal to what? AB was equal to CD. And at the same time, this AB now you got equal to BC. And BC was equal to what? AD. Now, can you say all four sides are equal? Yes. Therefore, ABCD is a rhombus. Actually, you have to write, it is a long proof because you have to add in the exam the first part. But as we are doing this problem already, I did not add the first part here, but you have to write this from your side completely. Right, so please note it down. Okay, no problem. Other few problems you will be able to do. Please do that. Then next day we'll be able to finish the problem of your book. but I'll still take two sittings to do extra problems as well.